This is Chapter 14 homework, starting with number 39. We have an initial pressure of 100 kilopascals, a final pressure of 75 kilopascals, constant temperature of 300 Kelvin. The question A is asking by what factor does its volume increase? So a way we can phrase that mathematically is to ask what is the ratio of V1 over V0? Since we're dealing with a change in pressure, and we know what temperature is, let's go look at the ideal gas law. PV equals nRT, something I taught you in an earlier chapter, was to arrange the ideal gas law so that all the variables are on one side and the constants are on the other. So in this case, PV equals constant, which means P1 V1 equals P0 V0. And then you can rearrange that algebraically, so you get V1 over V0 equals P0 over P1, 100 kilopascals over 75 kilopascals. There's no need to convert that to MKS units because the units, kilopascals, are going to go away. As long as they're the same unit, they'll divide out. And we're left with V1 over V0 equals 4/3. What that means is that volume increases by a factor of 4/3. Another way of saying that is that it increases by 33%. Question B asks how much work does the gas do? Well, since it's isothermal, we use the work equation. Work equals nRT times natural log of V0 over V1. Since in part A we found V1 over V0 is 4/3, we can say V0 over V1 is 3/4. Plug in the numbers. Because we're taking the natural log of 3/4, the whole thing becomes negative. So we have negative 215 joules. And since W, work done to the gas, is negative 215 joules, that means that work done by the gas, or the gas does, positive 215 joules of work. Next is number 42. Number 42, we have 0.10 moles of an ideal gas at 300 Kelvin. Gas expands isothermally. Does heat flow into or out of the gas? Okay, so I drew a PV diagram. It's nice sometimes just to be able to see what's going on. Isothermal expansion. And this reminds me of when a gas expands, work is going to be negative. So I say here that W is less than 0. Let's apply the first law of thermodynamics to figure out what's going on with heat flow. Since delta U equals Q plus W. So we solve for Q. Since it's isothermal, we can say delta U is 0, so Q equals negative W. Now up here, we said it's an expansion that W is negative, which means Q is the opposite of a negative number, so we can say Q is positive, or heat flows in. Part B says that the volume increases by a factor of 3. What is that heat flow? We already learned in Part A that heat flow is positive. Now we're looking for an actual number here. So based on the first law of thermodynamics, right here, we already solved that Q is the opposite of W. So let's bring it down here. Q is the opposite of W. Q therefore is negative nRT times the natural log of the ratios of the volumes. Since V1 over V0 is 3, here we're using V0 over V1, that's going to be 1/3. And you plug in the numbers and get that heat flow is positive 274 joules. Number 63 involves, okay, pretty easy one. A heat engine does 650 joules of work, dumps 1270 joules of heat into its cold reservoir. What's its efficiency? So let's see, in this case we have efficiency just for a heat engine. Remember, efficiency, or for refrigerators, coefficient of performance. Whichever one of these you're dealing with, remember it's always the good thing that you wanted to get divided by the thing that's invested, the thing you pay for. So in the case of a heat engine, it's the work you're getting out of how much heat is drawn from the from the hot temperature reservoir. Now, it's useful to have conservation of energy. Q sub H equals W plus Q sub L. So our efficiency equation, in the denominator, instead of Q sub H, we have W plus Q sub L. Plug in the numbers then, and you get that efficiency is 0.34. Let's try a little zooming here. Okay. Number 65. We have a very similar problem. You have your QH of 1700 megajoules, QL of 1100 megajoules. When you read the problem, it says this is each second. So each second that passes by, there's this much heat. Later on in part B, we'll relate that to the power. So you have efficiency is W over Q sub H, just like in number 63. Get that in terms of Q sub H and Q sub L. Where I get this numerator from goes back to the conservation of energy. And you should get efficiency as 0.353. Part B is regarding the work that's done. And we can use conservation of energy. Work is QH minus QL, divided by 1700 minus 1100 megajoules. So we get 600 megajoules. Now we go back to, in the original writing of the problem, it says that this is what's done every second. So it's 600 megajoules of work per second. The question is asking what is the rate. So we can say 600 megajoules per second or 600 megawatts. I think this is the one where in the back of the book the answer is given as 600 megajoules, but that's a bit of an error. It should be 600 megawatts because it's the rate. The last one for this part of the video, number 67. Very simple one. We're just looking at the two temperatures, two operating temperatures. You need to have those in Kelvin because they're absolute temperatures. The ideal efficiency is 1 minus TL over TH, and that gives 0.268.